they fly, they're leaving these streams behind them. Let's press play again. So that's pretty interesting. Now, what happens when we change the integration step? Well, let's just select the icon here, and I'm just going to change the integration step in the viewport to half a frame. You can see it's had quite a big effect. You can see the particles are veering off in this direction now. If I change it to a quarter of a frame, you can see it's had less of an effect. So by sampling the particles more frequently, we've picked up on some of the hidden detail that was actually inside that space warp. Now if I change it to 1/8 of a frame, there's a slight difference, not much. So you can see that increasing the integration steps with a very large curvy wind turbulence effect doesn't really have that much of an effect. It does when you go from frame to a half frame, but once you get down to a quarter frame and 1/8 of a frame, and if at render time you used ticks and so forth, you wouldn't really see that much of a difference. So by sampling more frequently, you can see it doesn't have that much of an effect on any sort of noise algorithms that have a large frequency. You're sampling a large frequency with a small frequency, and it doesn't really give you any more detail. So let's go back to frame 0, put the integration step back to frame, and turn on the second wind force. There we go. Now let's press play again and see what happens. You can see overall the particles are a little bit more chaotic. That's because in this case the wind force is now more frequent, and therefore it's affecting the particles on a much more frequent basis. It's perturbing their direction of travel much more frequently. Let's get the particles to a point which we're happy with, let's say there. And now I'll go to the source icon and I'll change the integration steps again. I'll change it to half a frame, and you can see they change a little bit. And I'll change it to 1/4 of a frame, and you see we still get quite a big difference. And then we'll change it to 1/8 of a frame, and again we're still getting quite big differences. That's because we're actually sampling a much more frequent noise pattern with more frequent samples in time. This means that as we go lower and lower and lower with our integration steps, we're sampling a more accurate representation of how that noise is perturbing our particles. So you can see that this is the second effect that the integration step will have on your particle system. It allows for greater fidelity in the way your particle system actually solves. Now, the other thing to bear in mind is, as you saw, every time I increased, or rather I decreased the integration step, getting lower and lower and lower, every time particle flow had to sample twice as many integration steps as it had on the previous setting. So obviously at 1 frame you've got 1 sample, at half a frame you've got 2 samples, quarter you've got 4 samples, 8 you've got 8 samples, and if you keep on going down you'll end up with 16, 32, 64 and 128. Basically jumping from frames to ticks, you get a much bigger increase in the amount of samples you'll have per frame. But if you've got very, very granular motion, like a very high frequency wind turbulence, you'll get a much more accurate result from it. Okay, let's move on to collisions. In particle flow, collisions between particles and an object need 2 to 3 items to work. To demonstrate this, I'm just going to create a very simple scene. Let me just get rid of this one first. I'm going to select these elements and delete those. Get rid of these space warps here and these space warps here. So what I'm going to do is I'm going to create a very simple flow. I'm going to create a couple of collision objects. Now these are not going to be geometry, these are just going to be collision space warps. So let's have a quick look at these. I'm going to go to space warps, deflectors, and I'm going to pick a deflector, which is just a rectangle which I can actually draw. There we go. And I'll just turn off grid so we don't get confused between the two. And then the second type I'm going to look at is an S deflector. So I'm just going to draw that here. Go into a side view and make sure it's actually lying on our plane. There we go. Go back into perspective view. Now let's create a particle flow. I'll just draw one in the viewport. Go to particle system, PF source. I'll keep it quite small. Go into a side view, and then I'll move it up in the air. Go back to frame 1, and I'll rotate it so it's firing out particles in the air a little bit. Okay. Now, one of the elements that we need for collisions, we've already made already, and that is a space warp. This space warp generates collisions based on its gizmo. You can see it's a spherical gizmo. It's actually using a mathematical representation of a sphere. So that's one type. The other type you can see is a plane space warp, and this will detect any particles that come into section with its plane. So there we are. We have some of the elements already to actually create a collision. Now you need some way to interface these space warps with elements with inside particle flow, and we do that with an operator, and forces also work in the same way as this, so I'll quickly show you that. If I go to space warps and go to forces, in this case I'm going to need gravity, so I'm going to grab a gravity space warp and I'm going to draw it here, and you can see it's using the default values for it. So let me now link these together within particle flow. I'll bring up the particle view and just minimize it so I can see these a little bit better. There we go. And you can see it's built, when I built this icon, it actually created a standard particle flow, and it's got its source here, it's got this event, and it's got the usual standard operators within that event. The position icon is fine, the birthing is fine, the speed is fine. Rotation, we don't really need that, so let's just get rid of that. And the shape, we don't really need that, we're not going to render anything, so we'll get rid of that also. What we do need is some way to link up this force, this gravity, into this event to actually make it take effect. So I'm going to drag a force operator into here. And now you can see I have a list here with which I can actually pick forces to add to this particular force operator. So I'm going to add this force here, and you can see now I've got gravity. Now through this operator, that force of gravity will be applied to the particles. This is a list, so you can actually add more than one force to one operator, but generally it's a good idea to put one force in each operator. That's because you've got an influence parameter here, and that actually allows you to control how strong that force is. And obviously if you have one force per operator, you can actually control each force individually using these influence parameters here. So generally it's a good idea to keep individual forces in individual operators. Of course, if you want group control over lots of forces, you can put them all in the one operator, and then you've got group control using the influence there. A similar system is used for collisions. Now collisions are tests, so we need a collision test. So here's collision. We'll put it into this event here. Now in the previous example we showed you where forces and collisions fought against each other and produced bad results. So you can see in this example I'm actually putting the force before the collision, and that avoids any problems with the force pushing the particles down after the collision has taken place. And this should result in nice clean collisions. Now the collision is looking for something to work with. It's exactly the same as the force. It needs a space warp to work. So you can see it as a list as well, and in exactly the same way as the force operator, you can have a list of collision gizmos to actually work with. So let's add the ones that we have already. Just adding these in. There we go. And I'm just going to change the parameter on these gizmos so that they don't actually do quite as much bouncing as they do by default. I'll just give them a little bit of bouncing. There we go. And I'm going to increase the friction quite a bit. And a little bit of variation in the bounce. I'll do that on both. It's a kind of way of simulating their surface characteristics, whether they're coarse or whether they're very smooth. We can create a little bit of chaos in the way the particles bounce. We've got some friction. I've got more friction on the floor than I have on the sphere, which allows the particles to fall down the sphere. And let's just quickly run through that and see if we get our particles flying where we need them, and see if we're getting a nice simulation. Well, by chance, as it turns out, our particles have actually flown